Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but you know, I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everybody. Hello. Oh, that is loud in my ears. That is loud in my ears. I hope it's not loud in everybody else's ears.
Hello,
it's just
everybody.
localized to us.
Yeah.
Sorry. Getting
So
off on a
good.
great start here.
All's good. Hello, everybody. Welcome to another episode of Ask Us Anything About Electrochemistry. I'm Alex. He's Neil, and we're both. I'm a chemist, and he's the chemical engineer at Pine Research Instrumentation. And we usually like to take some time on Fridays, Friday afternoons, to answer questions that you might have on electrochemistry. It's a difficult subject. We get a lot of questions through webinars, phone, YouTube video comments. And we figured this would be a good venue to talk about and really go into detail on some of the questions you might have about electrochemistry. So I think we're on, this is like episode 46 of Ask Us Anything About Electrochemistry. And during these sessions, if you're watching us after the live stream, we will have the questions as timestamps in the description below. So if there was a question that you'd like to know about or learn about, you can click on them directly after the live stream is done, or at least a few days after the live stream is done. It takes us some time to go through all the questions and write in the timestamps. We have found that in our over 45 episodes of making this this live stream, the best kind of questions to ask are questions that are kind of in the middle between either being way too specific, where we have no idea what the answer is, or way too broad, and it is perhaps better to watch, say, a webinar or a course on that kind of subject to answer that question in any detail. So questions that are kind of in the middle that have to do with a specific aspect of electrochemistry that seems a little bit confusing tends to be the best for this type of venue, sort of say. If you're a tier 1 or a tier 2 member, thank you for being a member, and you have the option to join us on Restream, which is our broadcasting platform. We broadcast to Twitter or X as well as YouTube, and you can talk to us, not just type in questions, but you can talk to us as well as share data or voltammograms or Nyquist plots that you're like, I have no idea what's happening or why this is the way it is. So basically that is that's the general format that we have. We usually do this for about 2 hours. And again, we just get names from people on YouTube and Twitter. So whatever your Twitter handle is, if we mispronounce it, we apologize in advance.
You apologize. I don't apologize for anything.
It doesn't.
If you have a funny name on YouTube, we will just butcher it, and that's just how it goes.
So there was so I don't know what you want to do. There's
I want you to answer that. I'm getting some materials. Yeah, sorry.
Okay.
I look like I'm ignoring Alex and everybody else, and it's just, to a certain extent that is true. But
Yeah.
I'm getting an answer to the Mott-Schottky question. I see. I have some materials I want to make a better answer. So if you want to tackle the question that we have from before, and I'll get myself ready for your. I'm sorry. Ephraim, I see your Mott-Schottky question. I will answer it after Alex answers.
Yeah. So we had a question earlier from YouTube from Samuel Calabumampo. Sorry again.
We did apologize.
We do apologize. I apologize.
You already you don't have to apologize. You already did it. It's fine.
Yeah.
That's right.
So I'm going to share. It's a long comment, but I believe that it's perhaps worth looking at. So hopefully everybody can see this. I will read this out loud. This question is with respect to IR compensation. I made a video about IR drop or IR compensation.
Do you want to share the Word doc? Sorry, because you're not.
Am I not showing?
It's not maximized. I maximize it now.
Oh, maximize
Sorry.
it. Okay.
It should be good now. I think.
Yeah, I'll make it big. Okay. That's also way too big. Okay. So this is actually a comment from maybe over a year ago. It's a response. And the general, I'll read this and I'll talk a little bit more about specifically what the initial question was about. Or actually, I'll tell you what the initial question was about. The initial question had to do with looking at the working reference and counter electrode as circuit elements and the resistance specifically between the counter and the reference and the resistance between the reference and the working electrode. So I'm going to read this question and then I'm going to go into some detail about the elements of the question and hopefully we can have this clarified. So first he says, thanks for your response from a year ago. I've been revisiting the video and comments and I have a new question about your explanation. We agree there is resistance directly between the counter and working electrodes, and that the counter electrode will drive current to the working electrode, and the measured and applied potential is only based on the reference electrode. Then, how do we determine the exact current flowing between the reference and the working electrodes to calculate the ohmic drop IR? The current flowing through the reference to working electrode resistance is only a part of the total current detected at the working electrode, since some of the current flows from the counter to the working resistor or resistance. For example, in a system where the counter electrode is closer to the working electrode than the reference electrode, the counter to working electrode resistance would be lower than the working electrode or the reference electrode to working electrode resistance. Therefore, most of the current would flow through the counter electrode to the working electrode, and the ohmic drop in the reference to working electrode would be negligible due to the low current is flowing through this resistance. On the other hand, I've seen people mention that the Lugin capillaries bring the reference electrode closer to the working electrode. However, the Lugin capillary is long, and the distance between the working and the reference electrode is usually larger than the distance between the working electrode and the counter electrode. I understood the Lugin capillary as a way to avoid contaminating the reference electrode or working solution. Okay, so there is a lot that is in here, and I will go back and forth between this and just kind of a description of the circuit. So let me talk a little bit about the circuit specifically, and this will hopefully help everybody make a little bit more sense of what we're talking about. All right, so I'm going to minimize this. We're going to go to review. We're going to start inking. So the system in question, we have a working electrode. Okay, and then we have a reference electrode. And then we have the counter electrode. This is kind of the diagram that I show. And the working electrode is commonly shown as a Randall's element or a Voigt element, but a Randall's circuit with a resistor and a capacitor in parallel. And then we have this RU, this solution resistance between the working and the reference electrode. So that's here. So the reference electrode is kind of this dot here. But then, and the counter electrode has the same thing, actually, just for completion. It has a double layer capacitance as well as some charge transfer resistance. It's not a very good picture, but that's okay. The main thing that the person's curious about is these two resistors, the RU, this guy, and the R comp, this guy. So this resistor and this resistor. Now, when I spoke to him a year ago on that YouTube comment, I had made a mistake. I had suggested that there is a separate, he was suggesting like, okay, you have, there are these resistors between counter and reference, and then reference and working, this RU and this R comp. But he was also suggesting that there is another resistor here between working and counter, that there's a separate resistance here. And that's actually incorrect. This does not exist. So that should actually go away. If there was a resistor between these two, between the counter and the working electrode, it would be equal to these two. It's the sum. It's the sum of the RU and the R comp, if we were to think of it this way. But there is no, to my knowledge at least, a parallel path between these. The resistance between the counter electrode and the working electrode is the sum of RU and R comp. All right, so that's one thing I want to kind of clarify, a mistake from well over a year ago. Now, there's another comment that he made in talking about this, and there were several things that need a little bit of clarification. And he's curious about how do we determine the exact current flowing between the reference and working electrodes to calculate the IR drop. And to address this, it's important to note that if I have any kind of circuit system, let's just say I have a power source here, and I have so there's some power, and then I have 2 resistors here. We can learn from physics that if I applied, say, 8 volts across this, and I had, say, like a 500 ohm resistor here, and a 300 ohm resistor here, that the current that flows, we can figure out what that current is as the sum of the series resistors. So the total resistance in this system, our total, is equal to 800 ohms. It's the sum. And that if I were to use V equals I times R, I would say, okay, well, the voltage is 8 volts, and the resistance is 800 ohms. And so my I is something like 1 milliamp. And that's 1 milliamp across the entire circuit. So there's 1 milliamp here, there's 1 milliamp here, there's 1 milliamp. The current, this is to say that the current is constant throughout the entire circuit, and that's the same in this as well. Now, the voltage across the 500 ohm resistor and the 300 ohm resistor is different. The voltage across here is 5 volts, and the voltage across the 300 ohm resistor is 3 volts, and that the total voltage is the same, is equal to what we applied. But the current remains the same. So the total current of your system, what's measured at the working electrode, the current, is just one number. And that's it. And that's the total current of the system. So that is a little bit of a misconception that current will be different at different parts of the system. Now, the amount of charge in different aspects of this may be different, but the current that flows will be constant. And that's the counter and the working electrode. So it's important to note that there is no, he also mentioned something that I do want to clarify, which is that it's weird to say, like, there is current that flows between the working and the reference electrode, but there's no current that actually goes into the reference electrode per se. The current really just flows through this circuit, and the reference electrode is really a point in between the working and counter electrode. So even if you do place the electrodes physically in different locations, and yes, you make this value very small or this value very large, schematically, the current does have to flow across the reference electrode for a measurement to be made. Like that's in a way how we make measurements. Voltages between reference and working is because the reference there's a position that the current flows across the reference electrode, the frit. And he was mentioning things about the Lugan capillary, which usually looks like this kind of big, something like this, actually. It's usually this big tube, and it juts out into a very small area, and the reference electrode is usually placed inside of it. And this is used to, you position this as close as you can to the working electrode, because in a way, current flows when you have this. The current flows across this. It doesn't go into the reference electrode here, but if the reference electrode frit, which is here, determines the kind of the position, like where it senses the point, it's going to be across this little opening on the glass of the Lugan capillary. And so you can adjust this position, sort of say, of the reference electrode by using something like a Lugan capillary. So I spoke a lot about a bunch of stuff, but hopefully that clarifies a few things. The current, again, the current is the same across the entire thing. So when you measure the current in your electrochemical system, you're measuring the total current of the whole thing. And the voltage may be different across different points. And that there is no separate resistor that's parallel to these two things. You will find that resistance is equal to the sum of the RU and the R comp, in the same way as if I just had a voltmeter with two different resistors in series. So hopefully that that answers that question. And
Chris looks like he asked a bit of a
follow up.
Yeah, well, yeah, as a maybe a corollary or something, just to let you finish the thought. What about the equivalent circuit model for the reference electrode itself? So I don't know if this is related to like that sensing point kind of thing we talked about a bit earlier. I don't know if you have a comment on that or not, or we just sort of move on.
The circuit. Okay, so when I think about a reference electrode, and Neil, you've talked about this as well, but when I think about the reference electrode, there is this frit. So there's a frit.
Are you drawing? You're not sharing.
Oh yeah, I'm not drawing. Oh yeah, I'm not sharing. Oh, hold on.
Yeah.
That's a good point. Thank you. I didn't draw very much. So okay, here we go.
Here
Frit, solutions, stuff like that. So the frit is ideally looked upon. It's porous glass, and it's treated as a resistor. It's treated as like a 1 k ohm resistor. Sometimes it can be higher. And one thing that Neil and I have found, that if you're doing impedance, the glass wall here actually acts as a capacitor. So in the high frequency regime, you have you actually have a capacitor that tends to be on the order of like 8 picofarads. So very small, but when it's very small, it also means it has a very big impedance. Of course, if you go fast enough in terms of frequency, this becomes the shorter path. So I think about the impedance of the reference electrode, or the equivalent circuit of the reference electrode, as a just kind of parallel here of like a capacitor and a resistor in parallel. And the vast majority of the time, there is a tiny amount of current flow through this resistor when making a measurement. That's always kind of required. But this current is like picofarads or less, because your reference electrode is connected to like a very high impedance electrometer. So if you think about like, all right, if I'm measuring like 1 volt, how much current is getting through 10 to the 12 ohms? It's a very, very negligible amount, but that's what's used to make measurements. So that's how I think about the equivalent circuit of the reference electrode. Hopefully that addresses Chris's what Chris was talking about.
Yeah.
Okay.
Okay, so I'm going to get to this. I have some slides from a previous webinar I've done, but Efreen asks, what frequency is usually used for performing Mott-Schottky analysis? So I'll directly answer your question, and then I will explain Mott-Schottky a little bit. We have a little bit of time to do so. So the short answer to your question is high frequencies, typically, usually in the kilohertz to tens of kilohertz. The slightly longer answer is that isn't a good idea, because very often it should not be done the way that it is commonly done. So now I will try to explain everything I just said. Okay, I got to do the thing where I share a presentation, and I have to show presenter view. I got to like share just the presentation, because it always takes me a minute to get here.
Oh, that's good.
The present. All right, so here's the slideshow. So help me if I'm sharing, Alex. I think I'm good, right?
Mm-hmm.
All right, so this is just a couple slides. I won't belabor this forever. Mott-Schottky is used to determine semiconductor properties. So typically semiconductors, unlike conductors, end up with this kind of interesting phenomena where you have your inner Helmholtz plane or your double layer capacitance when you polarize the electrode, and then there's this diffuse region some distance away because of the semiconducting properties. And there's basically no diffuse region. It's one of the characteristics, I suppose, of a semiconductor. It's not exactly relevant, perhaps, to Mott-Schottky, but it's just kind of because Mott-Schottky, as I mistakenly have said in the past, but essentially you're dealing with what's called a space charge capacitance, which is this capacitance in the semiconductor. I always have a hard time defining it or describing it really well, because I'm not a semiconductor electrochemist by trade per se. So I do apologize for not maybe being able to easily define everything like, just like that, right? I'm good with battery stuff and impedance, and Mott-Schottky, I have to work on exactly saying the right words. But for what it's worth, the Mott-Schottky equation you can see here, okay? And so it relates the space charge capacitance to a whole bunch of constants, including this ND, which is the electron donor density, and then the potential and the flat band potential, and then these are also constants, okay? And so what we do with the Mott-Schottky equation is we cast it this way. Basically, we have 1 over the capacitance squared, okay? And we have the potential. And so those are controlled / measurable things. And we can make a linear regression. So you can see if we plot y versus x, we get slope and intercept. And from the slope, we can get this ND, which is the electron donor density. Okay. And from the intercept, we can get essentially the flat band potential. These are properties of our semiconductor. Okay. And so from the slope and intercept, that's what we do. Now, this is to your point about what frequency we use. Now, what I said previously was that the most commonly done thing is high frequency. A lot of software programs encourage, I suppose, the user to type in one frequency, and you step the potential. So you do like 100 millivolts, 10 kilohertz, 50 millivolts, 10 kilohertz, 0 volts, 10 kilohertz, minus 50, 10 kilohertz. You step the potential, do a quick impedance measurement at one frequency, and then you move on. And then you plot the potential versus the measurement of the capacitance at each of those potentials. And you can get your constants. Now, what are the problems with that? I'll explain. So what you typically do when you do that, when you have one impedance point or like measurement, right, at one particular frequency, you either the classical way with a 1-point Mott-Schottky measurement is you fit either of these two circuits. You fit either a parallel, like a Randall's element, capacitor and resistor in parallel, or a series model. And sometimes in software programs, you'll see these things mentioned. You'll see the software might say like series or parallel. You pick one of them. Sometimes they'll show you both. It sort of depends on the software in the company, right, that you're using. But the reason that this is done is because you can actually, I'm not going to do all the mathematics out, but you can actually directly solve for capacitance. You have enough sort of unknowns and variables basically to do so. So when you do your impedance measurement, for instance, if you have a series, the bottom one here, the capacitance value, if you assume this is the circuit for that frequency, the capacitance is just -1 over the frequency times the imaginary impedance. And then this equation up here, minus Zi over omega ZR squared plus Ci squared. So you get ZR and Zi from your measurement. You plug it into either of these and you get a measurement of the capacitance. Okay. So that is what can be done. It's not what you should do, though. It tends to not be tremendously accurate. Okay. So one of the things that, for instance, again, I'll talk about it for my company because it's what I have the most, I guess, knowledge or experience with here. But our Mott-Schottky program, for instance, does not encourage the user to do a single frequency, which you can do. So you can see you can do a single frequency and pick one, and then do what I just described. But commonly, what you want to do is multi-frequencies, do a short range of frequencies. Okay. And so you might have some of that high frequency points, but you also want to go to mid to low frequency. You don't want to go too low because when you go really low frequency, you get a lot of diffusional stuff and it can impact your measurements. But basically, if you have really, really high frequencies, you might not really be probing all the capacitive behavior. It might be somewhat resistive stuff that you're actually probing, and the accuracy is decreased. And so to get some of those capacitive measurements, you really need to go to lower frequencies. And getting a range of frequencies also allows you, essentially, you're getting a slope of the Bode plot, and that allows you to get a more accurate measurement of the capacitance than just assuming one of those two circuits that I showed previously, which, you know, you're just assuming that this is what's happening in the model, and that's the space charge capacitance, and then that's your value. There's just a lot of error associated with that. You know, I can speak to what my company did in the past. Basically, we ran a series of experiments with some known capacitive elements and some semiconductors, and we tested it. And the level of accuracy diminishes greatly when you assume a single point and too simple a circuit in many instances. The accuracy increases dramatically when you are able to account for a small range of frequencies. So one of the things that happens is it does take a little longer because you have to do a short range of frequencies at each potential that you stop, you know, that over the range of potentials you use. But the result is that you get a much more accurate measurement, and you can account for things like non-idealities as well. There's a lot there. And the only other thing that I'll say about this before we move on to the next question is that I am in the process of preparing another webinar on this topic. So sometime as a teaser, spoiler alert, or whatever. That's not a spoiler; it's a teaser. That's the word. Teaser's the word. The wrong thing. I've done many webinars. You can find them in our YouTube channel as well. The recordings and things. And so the next one that I'm planning to do is a Mott-Schottky webinar to try to dig into this in some more detail and do some live examples and do some fitting and all of those kinds of things that go along with Mott-Schottky. So keep on the lookout. I usually tend to send out an email, and it will be posted, you know, on our website and things like that. So keep an eye out for that if you are interested in Mott-Schottky.
All right, very good. We got a question from Lav Patel on Twitter or X. And he's asking, could you discuss how to perform IR compensation? Love to.
So paused. I was wondering if you'd be like, no. Next question.
No, we can definitely do that. So Love, I guess there's a few things I'd mention, which is that the actual performing of IR compensation, relatively easy in the sense of just pushing a few buttons on your potentiostat. So just very simply, if I go to our Aftermath software, and then if you have a new experiment, say cyclic voltammetry, you can then go to the Advanced tab, and then there's working one IR compensation. You simply turn that on to manual, and then you can put in a resistance value, and then next time you do an experiment with IR next time you do a cyclic voltammetry experiment, it'll be compensated by 300 ohms. So that's how you would actually do it, but I don't think that's really what you're asking for. I think you want to know a little bit more about the steps that you would take kind of from start to finish, because getting the number of the solution resistance, I just threw 300 ohms in, but getting any kind of, how do you find that 300 ohms? So when you want to do IR compensation, you need to understand what is the solution resistance between your reference and your working electrode. So I did just talk a little bit about this from the previous question I answered, but we'll just look at the working electrode. So it's good to model the working electrode as a Randall circuit or a Voigt element or charge transfer resistance in parallel with the electrical double layer. And then you have this resistor here, and then you have your reference electrode, right? And so this RU is what you need to do IR compensation, right? You need to know what this RU is. So there are numerous techniques that you can use to determine the RU. There is EIS. There is something called current interrupt. Current interrupt. Or sometimes it's called CI. I'm just going to call it current int. There's another technique called positive feedback. These are kind of the three most positive feedback. These are the kind of three primary modes. You could say a potential step experiment is also another way of doing it, but it's based on the same principles of current interrupt. And so I actually have a video that goes into a little more detail about how to determine the solution resistance. So I can link that video. I can send you that video on Twitter, but basically that would be the way you could determine the solution resistance. So let me know if you want a little bit more detail as to how to determine this RU value. But once you determine it, so let's say you use EIS and you get something like, let's say you get 300 ohms. EIS gives you this value of 300 ohms, or if you're on a Nyquist plot, this distance from 0 to here is like 300 ohms. So that's how you could also view it. And yeah, Nyquist plots have that. So you find out that, okay, it's 300 ohms, but what you might decide to do is only use a percentage of the amount of resistance. You might not want to 100% compensate for this solution resistance because you run the risk of overcompensating. And when you overcompensate, you end up getting a lot of, you get very strange voltammograms that have less than 59 millivolts of peak separation for a fast reversible electron transfer. You also can get complete noise and lots of oscillation in your voltammogram. So you might decide to only apply something like 280 ohms. You might decide to only do 280 ohms of resistance, is what you type into the computer when you're actually doing IR compensation. So you need to determine the solution resistance and then plug the number in that you want, either the direct number with a percentage base, or the number that you want to be compensated for, and then just plug it into your potentiostat, and that'll work. So if you have more questions, or if you have more clarification, or if you request more clarification on that, please let us know. I think it's perhaps a very maybe too simple of an answer. But if you want more instruction about like, what does it mean, what is it actually doing, what's happening in your system, I'm happy to help with that too, or we are. Okay.
Chris has asked, related to the Mott-Schottky analysis, how does it relate to varactor diode effects? And you clarified a varactor, which I wasn't too familiar with either, is a reverse-based diode acting as a voltage-controlled capacitor. So it's basically a semiconductor PN junction that is biased to increase the depletion zone, which there's a relationship between that and the capacitance that it can have, basically. The short answer is that I don't think it is applicable at all, because a diode is by definition a device that permits current flow in one direction but not the other, which means it definitionally has a higher impedance going in one direction than in the other direction, which means it's effectively ineligible for impedance measurements. Impedance necessarily requires that the symmetry, or what the right word is, the impedance must be
linear, stable, causal.
Yeah, so it probably violates the linearity principle, I guess, was what you would say, because if you're doing impedance on a device, you polarize one direction, you polarize the other direction. It has to be the same. There is one impedance associated with that measurement, and so a diode fundamentally violates that, and so I don't believe it is applicable. Now, that is not to say that this varactor diode itself doesn't have, for example, because it appears to be basically a PN junction, which is a semiconductor, like a solar cell, basically, right? That isn't to say that construction itself doesn't have a electron donor density of some kind, or each of the p or the n side, don't, or have a flat band potential, or like all of those properties, I suppose, might still exist or matter. I don't have enough experience whatsoever to comment on that more. But as it relates to Mott-Schottky analysis and experimentation specifically, I don't believe that it's applicable for those reasons. And then it looks like Vinay has another follow-up on Mott-Schottky, which is how to select the potential window on Mott-Schottky analysis. Yeah, that's a good question, actually. The short answer is that you're looking for a window where the Mott-Schottky plot is linear. So let me sort of try to clarify. I'll open up PowerPoint here. Give me a second. I had my webinar up, so I'll get a fresh one to kind of draw on for you. Yeah. Okay, so when you do the Mott-Schottky, right, I just showed you the Mott-Schottky equation previously, but effectively what you plot is 1 over c squared versus E. Okay, and so sometimes it's what you're doing is just you do Mott-Schottky over like the entire stable potential window that you're in. Like if you're in an aqueous solvent, it might be like plus or minus a volt, right? Or 0 to 1, or I don't know, something like that. You might do the whole range. And like when you do it, you'll get something that's like, sometimes it looks like an S, just coincidentally. I don't know what significance exactly, but you'll do your Mott-Schottky over some big, it might kind of be flat, it might be whatever, but then it's like there's this, there's this window of potentials where it's relatively linear. And so you can restrict your Mott-Schottky analysis to that period of potentials, right, between, whatever here and here in this instance. Sometimes that's the answer. And then you're looking for things like, for example, if you do Mott-Schottky analysis and you get this kind of result, this is a positive slope, right? So positive slope, okay, that means you have an N-type semiconductor. And so if you do your Mott-Schottky analysis and instead you have the opposite, I'm trying to use different colors so it's sort of obvious here, and you have a negative slope, right? This right here is negative slope. And so predictably, right, P-type. So sometimes what you're doing is some of this comes with like you're testing a material and for instance, based on your knowledge of the material that it's a P-type semiconductor. And so you're going to do Mott-Schottky with, do 25 millivolt steps or 50 millivolt steps or 100 millivolt step. Well, pick something, right? Some of it's how long do you want to sit there for? And do a big wide window and look for where it's linear. And hopefully you get a negative slope somewhere if you're doing a P-type semiconductor or vice versa for an N-type semiconductor. And then apply your slope. I mean, to a certain extent, this might feel reminiscent of Tafel analysis. You're sort of looking for the slope where it's some number and that represents the kinetic region, right? There's a little bit of a parallel here as far as, using what you know about the analysis to back out information about what potential range or something like that. It almost feels backwards. Like you should be like, this is the potential range I should do. And then I'm going to get my slope from that range. Sometimes that is what I guess most of the time that probably is the order that you would wish to do, but you don't always know for a bunch of different reasons. So what I'm describing here is also common and not necessarily the wrong thing to do. And then the last thing I'll say is that sometimes different materials have odd behavior where they might behave like a P-type over some potentials and then an N-type over other potentials. And so what potential window you're looking for depends on what you're trying to study. If you're trying to study your material as it behaves like an N-type, you got to study it over here. If you're trying to study your material as it behaves like a P-type, you want to study over here, right? So some of that is whatever you're trying to look for with respect to your material. But it's generally speaking, if you do your Mott-Schottky analysis and you don't get any linear region or something's wrong, or you might have to check check some of the parameters of your experiment, or things like that, right? But yeah, ultimately you should be getting a Mott-Schottky plot, and there should be some region that's linear, right? I mean, that's kind of the simplest answer, I suppose.
All right. Very good. Looks like there are no questions right at the moment.
Yeah, Chris was saying, suppose you should have asked how those effects would show up in an experiment, indicating that Mott-Schottky is not valid. Yeah, so yeah, Mott-Schottky won't work too well on a diode, I suspect. I've never tried to do it, to be honest. The interesting thing with that is, I guess it's like, EIS is different than just impedance. EIS is a subset of impedance, generally speaking. Impedance is the application of a sinusoidal perturbation. Impedance is the application of a sinusoidal electrochemical perturbation, which is potential or current. You can have all sorts of impedance. And now the impedance of electrical components is also, potential and current, what have you. But the EIS is specific to electrochemistry and those kinds of systems, whereas diodes are just pure resistors or circuitry. Impedance, those are whatever solid state systems you'd say, right? So impedance itself is and has been used on those systems for a long time. And that's almost sort of a tangential kind of a field to, when we talk more commonly about impedance of like your glassy carbon electrode, right? Or things like that. So I just sort of say that as to say, the analysis of a diode or some of these other sort of electronic components is interesting and a bit like, I don't know, somewhat beyond my knowledge, I guess. I'm electrical engineers, I think, do more of that kind of stuff, I guess you would say.
Vinay has another follow-up saying, with increasing thickness of material, why potential window of the Mott-Schottky analysis changes?
That's a good...
Increasing thickness of the material.
So potential window changes. I mean, something is fundamentally changing with your electrode, seems to be the case, because in general, if you have the same processes occurring on any material, in theory, potential is independent of the size or the thickness of your material.
Yeah.
Right. So if changing the thickness is having an impact, then it's got to be impacting the behavior, like thermodynamically or electrochemically of the material, something like that.
I'm also asked. I'd also be curious, Vinay, what you mean exactly by potential window. It's to suggest that if you were to go beyond the limits of that potential window, something would happen. I mean, we just looked at a 1 over capacitance. 1 over the capacitance squared is the y-axis. So that is to suggest that if you move at a certain potential window that is bigger or smaller or something, you'd be changing something about the capacitance of your system. And it depends on what the thickness is. But generally speaking, the space charge capacitance is like, it can vary, of course. It'll vary on based on the potential, which is what the Mott-Schottky shows
doesn't work, right?
So the thickness. So basically, in that case, I guess that does make some sense. Of course, we're talking about thickness on a. I think it's on the order of
microns.
Microns.
Are you talking about the
space
capacitance?
Yeah, it's the space. The thickness of the space charge capacitance is on the. It's like 100 times bigger than like the double layer or something.
The double layer is microns, right?
The double layer is like it's like peak.
No.
It's like angstroms.
I'm thinking of the diffusion layer thickness.
Yeah.
So the double layer.
So the double layer, there's a double layer thickness. There is the capacitance associated with like just the layer of atoms that are right on the surface. But when it comes to space charge capacitance, there's a thickness here of how far do you get charge separation between the solution interface and then how far you can pull charge out. So in that case, that would make sense why okay, so thickness is in microns. So then if the thickness is getting bigger on the micron scale, it would make me think that you're able to get more charge separation and hence quote lower capacitance because 1/c² will be bigger. So that would affect the potential window because your capacitance would go off higher that way. So again, this kind of asks the question like, what do you mean by potential window? Because in potential window for non-semiconductor electrochemistry, we're usually talking about oxidizing or breaking apart solvent or the electrode material itself. But in this case, we're looking at that the y-axis is 1/c². So basically, I just want to make sure like, like maybe potential window is really, really big, like before something breaks. Like, I think that's one thing that maybe there's some clarification on. So yes, hopefully maybe that helps a little bit in understanding why the thickness of the material changes the potential window, because the capacitance is changing. The space charge capacitance. All right, so I guess moving on. Of course, Vinay, let us know if you have more questions. But let's see, we're getting a question, which is, what is the turnover frequency? TOF. Turnover frequency it's usually a phrase commonly used in analytical chemistry. It's usually described for things like catalysis, for example, how often you can have a thing cycle numerous times before it, or actually the number of turnovers, the number of times it's doing a cycle, a kinetic, maybe a kinetic type of experiment or a reaction, how many times it's doing that per unit time. Is just the turnover frequency, and it's used a lot in catalysis with.
It's like an efficiency.
How many times,
right? I mean, it's like,
yeah, it's like how many times does a thing do something per unit time?
How many times does your catalyst transform the reactant into a product per unit time?
Yeah, and turn over. It's just turning over from like being oxidized to reduced and back and forth.
Yeah.
How quick is that? So hopefully that was helpful.
Simple answer, but
simple answer.
That is the answer.
That is the answer. Okay.
Yeah.
So if you want, if there are no questions right now, I can speak a little bit about a question that. Oh wait, no, we got a question from Ferris Whitehouse. Good to see Ferris.
Yeah, good to see you again, Ferris.
Let's see.
Is there an ideal method for holding carbon cloth or carbon foam in a cell? Are there any important considerations when choosing between, for example, a graphite clamp or using a silver wire and paste? The carbon foam and carbon paper is tough because it's brittle. So when it comes to holding brittle carbon stuff, this is my suggestion. Let me share. So effectively, when it comes to brittle carbon things, what you want to get is something that's like plates that clamp on either side of it. So if you have carbon, again, foam tends to be pretty brittle, like paper tends to be pretty brittle. Okay, so what you want is whether they make devices like this or you make one yourself, it depends. You want to get something that like, let me get a side view of this. So if the side view of this thing. So you'll get something at the top, not an alligator clip. We're talking about two sort of, almost like pieces of some kind of metal or whatever. Okay. And you're going to like press these together and they'll, clamp on it, but in a flat way. And then you'll only dip it in solution, at some known level, or you can coat this part with Teflon tape to insulate it or something like that, right? So you're trying to control the amount of, because you don't, in all cases of using a substrate that you're trying to clip and use as an electrode, you don't want the thing clamping it to be part of the electrode, right? You want just the carbon with your stuff to be your electrode. When it comes to carbon cloth, it's not brittle. So often you can use an alligator clip. Now they make alligator clips, for instance, right? Typical alligator clips can be tough because they have scary teeth. Like this. Teeth. And they're usually very much this scary, where it's a scary dragon and it breathes fire. So, okay. So if there's, sorry, I'm a child. So if there are teeth on it, you have to be careful, because seriously, that these teeth can rip through the cloth. It can cause fibers to escape. You can have some problems like that. They make alligator clips. Sometimes they're like little copper ones, like we sell one, where it's like a flat, right? It has a spring-loaded kind of a thing, right? Something like this, right? But it's this surface is flat in here, so you can put your carbon cloth in and then clamp it. And again, you'll only dip it at some level, so you don't want you don't want to have this part be part of the electrode. So you can sometimes insulate it with Teflon tape or whatever, or you just make sure that it's out of solution. Something like paste, epoxy, copper conductive, something silver conductive, should only really be necessary if what I just described isn't possible, where it's like you don't, and I'm sort of making an assumption that your setup is that you have something dipped from above into solution. That may not be the case, right? It may be different geometry, morphology going on. And so if that is the case, then some of this might not be perfectly applicable. Of course, that being said, it is possible to use something like silver wire, paste. They make copper tape. For instance, copper and silver are, of course, good choices in general, because copper and silver, I believe, are the two most conductive metals that we know of. Silver is the most conductive, I think, metal intrinsically. And so anything silver is going to be good. It's not going to add a ton of resistance to your system and anything like that. Copper as well is easy. So you can get like copper tape, and you have your potentiostat or your power supply over here, and you have to connect the leads with some copper tape to the cloth, whatever orientation it's in. That can also be done. Again, it's more like you're clamping it somehow or sticking it in a way that it will be less likely to damage it, and make sure that it is not ending up, in the solution, and be wary of those things, because with carbon cloth or carbon foam or carbon paper, it's not, if you're working in aqueous, for instance, it might not be too big of a problem, because carbon is hydrophobic, and so it's not tremendously likely, I would say, to wick up the carbon itself, right? But if you're working in non-aqueous, it might. You'll get that's not capillary action, just the hydrophobicity or hydrophilicity, essentially. You don't want to get solution to sort of creep its way through your, material into the clip. Because again, if there's any connection with electrolyte to the clip, to the paste, to the tape, whatever, that's now part of your electrode. Right. And you might get weird electrochemical results. You might get more product or less product or something. And it's like, well, that's not attributable to what I want. That's attributable to the copper alligator clip, which is not ideal. You're not looking to make a device with a copper alligator clip. You're looking to make a device with carbon paper in your novel material or something like that. So be careful, mainly, no matter what you use, of the strategies that I mentioned, that your leads and or connectors, right, are not part of the electrode in the solution. That's the main thing that you want to try to avoid, I think.
All right. Yeah, Chris just had a quick comment that you may want to clamp the edges in a non-conductive frame for mechanical stability.
Yeah, that's
well.
probably a more robust application of what I was saying. Like, the cheap, more accessible way might be to like wrap stuff in Teflon tape, right?
Mm-hmm.
If you have a more robust frame of, Teflon or whatever, right, non-conductive insulating material, that might be a more elegant solution. But for sure, having something non-conductive as part of the connection to insulate against, having your, electrode include some extra stuff is ideal. Ferris, the carbons I'm testing are pretty durable, so that's good.
Mm-hmm.
The silver wire paste gives low resistance. I would expect that. Seemed like the silver is reacting a little bit and throwing off the middle. Yeah, exactly. So it sounds like mainly your problem is getting the silver out of the electrode. So it's an insulating thing. So you're going to have to limit the amount you use, limit the reach of where it's used, limit how much of your electrode is exposed in solution. All those kinds of things, or you're going to have to use something different. And don't be discouraged if you don't have to use silver. Like, silver's going to give low resistance because silver is tremendously conductive, which is excellent, right? But if you have to move to something a little more controllable, because maybe the paste is, it's paste, it might spread accidentally, or, you might have a tough time getting physically like the paste just where you want it. It sort of spreads, and then it's part of your electrode. It's thrown off your measurements, of course, because you're getting silver electric catalysis. You don't want that. Silver's also a good electrode. So you may have to experiment with some other things. Tape or clips are probably, they're perhaps in many ways easier to control the size and the geometry than a paste. Paste might flow and get kind of where you don't want it, things like that.
One thing that may also help, I did this in grad school. It was a bit messy, but if you're using the silver wire or silver paste, you can use something called Torr-Seal epoxy. And it's a fairly electrochemically inert epoxy that you can put over it, and it's an insulator. So
it goes over the paste.
Yeah, it goes over the paste.
Cool.
So it's like an arts and crafts project. I posted the Amazon link to the epoxy, but cool. It does take time. It's like you set your whole thing up, you put your silver epoxy on, you hope that it cures, and then you put Torr-Seal epoxy on it. You have that to cure. And then at that point, it's like, okay, it's usually pretty tight, and it's Torr-Seal, so it's meant to be like pressure vacuum safe. But at the same time, if you ever want to get that carbon paper back to do something else, and you want to remove it, oh, good luck. It's stuck. So
yeah, it's stuck
something
there
to keep
forever.
in mind. Another option.
Oh, that's cool.
And then Chris mentioned whether or not gold plating the edge would be a viable option.
Yeah, possibly. But again, you're just putting one problem for another, and potentially, right? Gold is also electrochemically active and could become part of your electrode. So if you get gold on there, you just have another problem that you might end up having accidentally gold interfering with your experiments now. So it isn't to say it's not a possibility, I suppose, but it might not exactly work if the problem is getting stuff out of your electrode, right? The whatever. So yeah, that epoxy is a good idea. I wasn't aware of that.
Just another thing. Yeah, it gets super messy.
Yeah, it really is arts and crafts.
It's arts and crafts.
Most of a PhD is just arts and crafts. It really is.
Yeah,
ultimately.
Yes.
Yeah.
Yeah, it is. Looks like there are no
Yeah, what were
questions.
you were gonna talk about a thing?
The only thing I was going to mention, I don't have the person's link, but or the person's name, but they asked if we could spend a little bit of time going over like interpretation of cyclic voltammograms, like how do you interpret a cyclic voltammogram? And I forgot the person's name. I apologize for that. I will preface this by saying there are some textbook, like what does the information in a CV mean, and then there's the actual. I've been doing lots of electrochemistry and a lot of different electrochemical systems, and I've seen lots of cyclic voltammograms, and you just gain an intuition for what is happening in your cyclic voltammogram. So some of this, there's some fundamental electrochemistry, but some of it is like, oh, what does noise look like? What does electrochemical noise look like? What does it mean when you have a double layer capacitance, or if something's irreversible or something like that? And that kind of comes with time. But I can share, at least generally speaking, a little bit of just showing you a little bit about what cyclic voltammograms look like until at least we get another question, and we can, and until then I can talk a little bit about how you interpret a cyclic voltammogram. So to do this, I'm using Aftermath Live. It's this electrochemical simulation software that we have, and I'm doing a very simple one electron transfer reduction, sweeping the voltage from +1 to -1 volts, and the redox potential for this reduction reaction of A plus an electron going to B is at 0. So this is kind of the E naught of our system. And so this is a very typical cyclic voltammogram. This is actually a perfect cyclic voltammogram. You will almost never experience this in your time doing your PhD. But when we look at voltammograms like this, what these peaks correspond to is, in this case, the diffusion controlled current or reduction of A going to B. So actually, if I play this as an animation, as we go from +1 volt to -1 volt, as we get closer and closer to the E naught, the current increases dramatically, and the corresponding surface concentration of my species A and my species B, A is red and B is blue, will change as a function of time, but as a function of the potential. And as we start to sweep back and we oxidize B back to A, we then get this switch. The B goes down, and then A is now kind of regenerated here as at the surface over time. So if I look at the surface concentration profile, it'll look something like this. I'm going to play this one more time because the surface of the electrode is full of A initially, and then eventually over time, the surface concentration starts to decrease. This is, again, as a function of time or a function of length. So what we see here is the diffusion layer thickness basically growing as a function of time. And then eventually, again, we're doing the same kind of cyclic voltammogram as we then go to more positive potentials, and then we oxidize B back to A. The surface concentration right at the electrode switches right back so that we have all A and all B. But there's still some A and B some distance away from the electrode, but not at the electrode exactly. This is the most kind of, and I'm doing this relatively quickly, but this is the most ideal type of voltammogram in terms of how to think about it, how to look at it. As you move to slightly more complicated systems, I want to get this up. As you move to more complicated systems, and why can't I change this? I want this to go up, but I can't because Restream is in the way. Oh, here we go. I can hide that. There we go. I can change things like the double layer capacitance. And so one thing you'll notice is if you start to increase, so this is an ideal voltammogram, but if I say this is an exaggerated amount, but if I add a lot of double layer capacitance and I simulate, you'll notice that the thickness here starts to increase. And so this may start to look a little bit more like a real voltammogram that you would experience, because there's actually some kind of thickness to the electrical double layer charging, especially if you're working in, say, an aqueous medium where double layer capacitance is pretty high. You may also have things like solution resistance, where you'll see a tilting of the voltammogram. So if I go back to our perfect voltammogram and I add something like solution resistance, you'll notice that this starts to tilt. So anytime you observe peaks in your voltammogram and there's some tilting that might be happening, it could be due to solution resistance. But conversely, you may also observe that, well, it might not be solution resistance, it's actually slow kinetics. This K naught is the heterogeneous rate constant. If I were to make that smaller, you'll notice that the peak separation will start to move farther and farther away. And of course, it usually requires several orders of magnitude to really see the difference. But once you start to see these kinds of voltammograms and these kinds of shapes, you'll be able to identify what the peaks mean, what the peaks are doing. And really, when it comes to, and this is just a one electron transfer system, more often we find ourselves working with these kind of EC mechanisms, an electron transfer followed by some kind of chemical step. And if you have things like irreversible kinetics, you're going to start to see only one side of the reaction, or only a little bit of the reaction on the return. I think I need to go here, and then I just make it a little bit more. Let's see, simulate this. Yeah, I start to see a little bit more favoring one of the the products than the other, and I see just a little bit when it's reversible. So this is something I definitely observed a lot of it when I was in graduate school, just seeing these weird voltammograms that have like little tiny return waves, or more pronounced or slightly tilted other redox waves. And so it really takes time. I would also recommend using Aftermath Live to actually try to simulate weird voltammograms that you observe, and try to see whether or not you have an electron transfer or a chemical step, or two electron transfers. A few weeks ago, I was working with a colleague. We had a molecule. It was TCNQ. TCNQ has looks kind of like this. It has these two reduction waves that are like pretty far apart from each other. But because I know that it's like, okay, it's two sequential electron transfers, I can model it, and I can understand what each of these peaks really mean, and if there's kind of peak separation or sloping from these two, I can look at it or anticipate it. So to the person who made the YouTube comment about how to interpret cyclic voltammograms, it is a long kind of arduous journey, sort of say, and for that, I guess I wish you the best of luck. But using a tool like Aftermath Live can be very, very beneficial. Just it's relatively inexpensive, and you can play with all the parameters to see what does your voltammogram look like if you adjust the resistance or if you adjust the capacitance, and you can start to see, oh, my physical system looks like this. When I simulate it, I can get it to look like it. Maybe it those things that I'm simulating are actually what's happening in my experimental system. So that's something I wanted to brief crash course on how to interpret some voltammograms.
That's very good.
Yeah. So I think we haven't gotten any new questions, right? So
yeah, I think we've got some people watching on YouTube and on Twitter, but if anybody has questions, you can type them in. If I think sometimes I've found in Twitter, you can type chat, or it's not a comment, right? It's like a chat. It's actually a chat thing.
Yeah.
So you should be able to type your questions there. If not, you can migrate over to YouTube and type your questions there.
Mm-hmm.
We'll hang out a little while longer, and then if there aren't any questions, we'll wrap it up for this week.
Yeah.
But we do like to give it a little bit of time, because I know that there's a bit of a delay from what we're saying now and when everybody hears it. And so, so, when we see your question is when you wrote it, but also you're going to hear us read your question like 20 or 30 seconds later. So
yeah, that's also true.
We try to give a little bit of buffer time. in that regard. But yeah, so and typically this is the time when we get the influx of questions in the last.
Sometimes you do,
yeah, like 20 or 30 minutes.
Just random.
Yeah, it's tricky. I'm not sure what the different people in different time zones, when your active period of searching through YouTube for things to do is, or whatever. Everybody's got their, or it is. Oh yeah, I guess it's Easter weekend, so this is a holiday week. That's an interesting thing. Actually, I talked to a friend in Europe yesterday. Telling me that in Europe they either have Friday or Monday off, or both, and that's just not common here. It's not common in the U.S. to have a day off around Easter. I've never really had that.
We have a customer at North Carolina Central, and I was going to visit him on Friday, and he said that he was closed. They were closed on Friday because of the holiday. I'm like,
oh, interesting.
Wait, what holiday? And then I'm like, oh, it's Easter. I had no idea.
So maybe there is some of it. I don't recall there being. Maybe there was, and I just remember. And I worked in a government laboratory, and we maybe got a day. I don't remember. I can't remember if there was, but it doesn't. It never seemed like, maybe because it's Easter's on a Sunday, so it's not a work day. It's not an obvious day. Like we're if whatever Christmas or the 4th of July, typical American holidays are on a Tuesday, you get that day off or whatever it is. Whereas Easter is always on a Sunday, so it's not a work day for most people that work Monday through Friday, right?
Yeah.
So it's never felt like, for me either, like a holiday that I would remember to have a day off or whatever. But I guess in a lot of Europe and parts of Europe, they have Monday off for the day after or something like that. That's common. So I was just like, because they're asking me like, oh, do you have Monday off? I'm like, why would I have Monday off?
Yeah,
like, and I totally don't even get it. Like, what even ask that question?
Is there a holiday I'm missing here?
Yeah, I'll take Monday off. Am I allowed to? Is that a thing? Can I please? Yeah, Ash Wednesday and Good Friday. So this past Wednesday was Ash Wednesday, or was it?
Oh,
is that right? Yeah.
Interesting.
We're very knowledgeable about this topic.
I am not very knowledgeable.
That's definitely the case.
It's not electrochemistry.
It's not. It's right. But we're just killing some time and while we wait for some questions. Actually, Ayman has asked a question. Do you suggest taking a levels chemistry? I'm not sure I know what you mean. Is that can you clarify? I don't know what is a levels chemistry. Are you talking about courses, or is this like a university course thing? I don't know. I'm not familiar with this terminology.
Yeah. And
I do suggest taking chemistry. Take chemistry class.
Take chemistry class.
It's good for you.
Yeah, I think it depends on what you want to do. If you want to get into this crazy subject and into this field.
Chemistry, yeah, I don't know. Yeah, I think I'm not exactly sure what you mean. But you can clarify if you want to.
Yeah.
While
clarify.
We contemplate whether or not we should even be here today, because this is a holiday.
It's technically a holiday,
and that means that we should not be here. We should tell our boss that we're just leaving.
Yeah. What was it? Didn't we learn on our website? It actually said that we're open Monday through Thursday. And we had no idea.
Yeah. Somehow, probably shouldn't publicize, but it's kind of funny. Yeah, our website was like, oh, we're only open through Thursday. It's like, oh, I guess I'm just gonna take every Friday off because our website says we don't have to work, right? That's how this works. So if I change our website to say that we're open like Tuesday through Tuesday from,
Tuesday through Tuesday, we're open every day.
No, like Tuesday at 10 a.m. until that same Tuesday at 10:04 a.m.
So we're a whole
we work 4 minutes a week.
Yeah.
The website says so. So that's when I'm going to work.
That's what you're going to do.
But I expect full pay, just to be clear. That's what I do expect.
Let's see.
A levels. Oh, like
European secondary.
Like capital A, not like a level, like which level, a level. So you mean A levels.
I don't even know what A levels is.
Yeah, that must be, is it an Asian or European designation that I'm not familiar with? It must be. We have, obviously different courses and structures and the way we name them or what have you here in the US. And I don't know what A levels chemistry is.
It sounds just a very quick search. It just the equivalent for the U.S. would be the advanced placement courses.
Oh,
maybe. I'm taking a guess. Are
AP.
A levels recognized? A levels. So
so I took AP classes when I was in high school. Advanced placement. And I did recommend it. It was actually very useful for me. I took, for example, AP levels, like classes when I was in high school for chemistry, mathematics, and English. And I took the tests when I was probably a senior or whatever it was in some of those courses, and I got college credit for it before I went into college. So like my freshman year as an undergraduate, I didn't have to take, it would have been, I guess, calculus, like calculus 1 or whatever the day. I forget exactly which course it was, but I had AP credit from high school, so I didn't have to take a class that I, knew the material already. I got to basically use my AP credit. So, and same for an English credit and a chemistry credit. So, so I don't know if that's a similar kind of a system in Europe or in Asia, if you have the ability to sort of get prior credit to going into university. I found it nice, because then you can get credit for stuff that you would otherwise have to take, which, fair enough. You got to take, the university gets students from all over, and they have to make sure that your stuff, okay, not every high school is the same, and okay, so that makes sense. But it's certainly helpful if a topic to not have to take a class on it again and have it be boring or redundant. You could fill that time with a different class with new information. So I think it's a cool idea. I liked it personally. So, but I don't know if that's the same as what you're asking.
Yeah.
Dooley's is back. Am I familiar with how Marcus-Hush theory is relevant? What's Marcus-Hush theory? So the answer is no. I don't know what that is.
So
Marcus-Hush, did you look it up?
Yeah. So I'm used to Marcus theory.
Is this a chemistry thing that I wouldn't have learned about?
I mean, you may have learned about it.
I don't remember
it. The general idea behind Marcus theory, it's one of the most prevalent electron transfer theories. Basically, putting you have these two things on like these kind of energy diagrams. Like you have like one state and then you have the other state. So you have like the oxidized state and you have the reduced state, and they're these kind of U's. And then once the U's kind of overlap, you give it a. You know what? Why am I making these signs? I can just try to.
It's way better to draw in the air with your hands.
So much better to draw in the air.
Yes.
And trust me, I still try to like read more about Marcus theory to get like a better understanding of it. The guy I think he won a Nobel Prize or something for this. But the idea is, I guess in a simple sense, you have these energy diagrams.
And there's
overlap between them. So you have like, let's just say this is ox and this is red, and red. And basically you have these overlaps. So you can adjust. So when you have potential, so I guess to answer Dooley's question directly, yes, Marcus-Hush theory is very relevant to electrochemistry. It gives you like we usually talk about Butler-Volmer kinetics, but Butler-Volmer plus Marcus theory or Marcus-Hush theory is important in getting a better, a more complete understanding of like electron transfer. But this is energy on kind of the y-axis, and this is like you could call this reaction coordinates, I would say. Reaction coordinates. But the idea is that as you adjust the potential here, you're moving this up and down like relative energy. So if you have more states that are kind of overlapping, so let's say if I have this kind of like same thing but dotted this way, and then this can kind of goes up. it's a lot easier. I have so many more states here that easily kind of flow into this level of the reduced form. So when I increase this energy, it makes this go down, and then when I decrease this energy, it makes it much harder for only a little bit, right? If I bring this like down, like only a little bit, only the molecules that get to this energy are able to transfer over to like the reduced state. So so Marcus theory is very, like, at least our conceptual understanding of it's very true, but and I don't know an exact example. The most important thing about Marcus theory, and I don't know if he's asking any other like further questions about
just how
this.
it relates to electrochemistry.
Yeah, I mean I guess that is how it relates to electrochemistry. It's another view or description of electron transfer. And the most useful and interesting thing about Marcus theory is that it describes what's called the Marcus inverted region, which is when you move the potential so far up or down one of these that you so for example, if you think, okay, if I want to oxidize something, I ramp up the potential. And if I keep ramping up the potential with and there's no mass transport limitation or something, let's just say hypothetically, if I keep ramping the potential up, I should increase the kinetics indefinitely. But eventually you will actually slow the reaction down. And that's because of the Marcus inverted region. And it's some movement of the coordinates where this goes where this basically goes way, way, way up. Like this whole thing goes way too high up, such that this part touches this part, or it goes over that. So it's a way of explaining, hey, why don't I just increase the potential like dramatically? It'll keep going faster if I have no mass transport. Well, no, you'll eventually hit the Marcus inverted region where this guy is over here and this guy, goes to a spot where the kinetics are no longer favorable and the reaction rate actually decreases. So that's like the important thing of Marcus theory.
So is this basically somewhat of a mathematical, I don't want to know what to say, counter argument or to Butler-Volmer kinetics? Because mathematically, I understand what you just, that's a the description of how that would eventually lead you to a place where there's reaction coordinates for both the oxidation and reduction, and then you're not pushing the reaction anymore in that direction.
Yeah, it actually slows down.
Right. That's in violation of Butler-Volmer, strictly speaking, because Butler-Volmer is infinitely exponentially growing if you increase the potential. So, so is it sort of like a complement to Butler-Volmer that explains the extreme case, something like that?
I think so. I think that I'd like to think that Marcus theory came out after. I think it came out after Butler-Volmer. It's usually described as a complementary theory.
1956.
And Marcus theory was because Marcus theory is really like electron transfer reactions. So Marcus theory is used beyond electrochemistry, but it's definitely part of it. A lot of people use it for just like, if you shoot like the quintessential example of a Marcus theory system is when you just have iron 2 plus and iron 3 plus. You put both of them in solution. You put two different amounts of it, and you have a self-exchange reaction where the 2 plus reacts with the 3 plus and the 3 plus reacts with the 2 plus, and they just keep giving electrons back and forth. It's the most fundamental type of electron transfer. And then he built and grew the theory beyond that. The other aspect of Marcus theory that's important is the effect of solvation. So that there was actually, when we were developing Aftermath Live, there was a thought of having both the heterogeneous rate constant as a way to describe kinetics, but also lambda, which is the symbol that's used for solvation energy from Marcus theory, and like which one should we use? And it's like, well, everyone uses heterogeneous rate constant. So I think Butler-Volmer is a very broad, like it just assumes like it's a very broad, open type of theory, and then Marcus is a little bit more like I would say detailed.
So just to back up what you said, that does appear to be correct. So the basically paper published by Max Vollmer in 1930 is apparently where we derive the Butler-Volmer equation. It was based on earlier work by John Butler.
Okay.
So that's 1930, and the Marcus theory is from 1956.
Yeah.
So what you said is correct. It's Butler-Volmer is more of a general baseline of electrochemistry, broadly speaking, and kinetics, more specifically speaking, and then the Marcus theory was I guess
yes,
more work off that in regards to what you described.
Yeah, I think Rudolf Marcus is still alive. He is 100 years old. Holy cow. And he won the Nobel Prize, I think, in 1992.
Tremendous.
Yeah, it's just like a legend that's still alive.
Max Vollmer died in 1965.
Yeah. So it's like these theories came out. Like
Butler, I believe. Yeah, Butler died in 1977. So Butler and Vollmer are no longer with us.
Yeah.
But Marcus
is 100, which is amazing.
Oh, that's
and he's at Caltech.
Oh, cool. He's in Caltech.
He's at Caltech.
That's fascinating.
Okay, but yeah, Dooley's continue to ask us questions. I still want to also learn more about Marcus theory.
That's cool. I was not aware of that. I think that's one of those things. I'm from chemical engineering.
Well, yeah.
So a lot of the fundamental chemistry things, like I just wasn't covered. I took like organic chem and PChem and stuff like that, but like I didn't take as many pure chemistry curriculum courses as you did, for example. I had engineering courses are just different. So a lot of those kinds of things, a lot of times I'm like, I don't know what that is.
I didn't hear about Marcus theory until grad school.
Oh, interesting.
Yeah, so I don't even know if it would be covered. I don't even know if it would be covered in undergrad.
It's probably a little bit more advanced, right?
Yeah.
BMB is asked to suggest a book of electrochemistry. So Bard. Oh, except Bard. Oh, darn, I was so close.
There's another one, Conway. Conway.
Jeez, man. So the short answer is that I don't think there are many, if any, for what you're asking about, which is like a basic beginner's guide to electrochemistry. I really don't think it exists.
We have other books we can suggest. I don't know how basic they are. I always recommend Bill Heinemann's book. Let me find it. It goes by William Heinemann.
It's not particularly basic, I don't think, is it? Is that the practical? What is it called?
Yeah, it's called Electroanalytical. Let's see, electroanalytical methods. Laboratory techniques in electroanalytical chemistry.
How do you spell Heinemann? H-E-I? H Heinemann?
Yeah, Pete Kissinger. It's Heinemann.
Yeah, I used a Y, that's why I wasn't finding it. Yeah, laboratory techniques in electroanalytical chemistry. Yeah, again, it's
post that one.
You post it. That's a good book, I think, as well. But it's I feel like this question is and correct me if I'm wrong, or maybe don't correct me, and I'm just gonna say it anyway. I feel like this is a very common refrain that people are looking for this, like the most basic kinds of things, like I just need to know in plain English, like what are some of the basics of electrochemistry? Tell me what the Nernst equation is. Tell me what the Butler-Volmer equation is. Whatever, right? Don't talk about Marcus theory. No, but like experimental, practical electrochemistry. Like start by doing this. Dump your electrode in the thing. Get a beaker. Fill it with salt. Like I don't know, simple stuff. I feel like that generally speaking doesn't exist, and perhaps there's a reason for it because maybe no one's ever thought of it, or because these things are fleshed out in graduate school or whatever, and you just sort of end up, everyone stumbles through graduate school research figuring it out on their own. But I think that I feel like there's a gap there, I'll be honest.
Yeah,
for like really, not patronizingly stupid, but basic practical electrochemistry seems like it's kind of missing. Vygotsky.
That's what
I don't know that one.
I don't know that one either. So let's see. Vygotsky fundamentals. I don't spend that much time reading reading electrochemistry books besides Bard and Faulkner, which is this one that I keep around. Which we all keep around. He said
not Bard.
He said not Bard,
yeah.
But I haven't looked at Vygotsky. I definitely believe that there are it's coming from like the Vygotsky, so it's like the Russian school of electrochemistry.
It's probably complicated.
Electrochemical Society. Oh, what is this? 1930. Oh, I'm looking at you know what? Maybe one day.
First published in 2005.
Yeah, so maybe it's a relatively new book. Okay, I mean, if it's a relatively new book, I think maybe give it a shot. It's also not ultra expensive.
It looks like it's similar to Bard and Faulkner. I mean, just based on the table of content sections, it's like electric currents and ionic conductors, electrode potentials, thermodynamics of electrochemical systems, mass transfer, phase boundaries.
Yeah,
it's like,
let's see if we can.
Just seems like another version of Bard and Faulkner, essentially.
Yeah,
just at quick glance.
Just a minute. Yeah, I'm also doing a quick glance. Yeah, it even has all the symbols and stuff.
I mean, to me, I think it's like the tricky thing again is my impression and experience has been that people are looking not just for something like this, which has good information, theoretical electrochemistry, but practical kinds of advice, on research things, which is why we're doing this live stream every week, I do think to a certain degree there's a gap for what I would consider, let's try to say it in a not mean way or something, but like dumbed down practical research kinds of things, because you just sort of don't know until you know. And to a large degree that comes from your own experience in the laboratory, but to have something that kind of just gets you started, I think would be useful for a lot of folks.
Yeah, I agree. I think so. One of the things I've always found difficult with learning electrochemistry and like reading books is that you're going to read something and you're going to have absolutely zero clue what they're talking about. I'm looking through this Vygotsky book and they start off with just like, let C sub K be the original concentration of a substance, K, E of the compound, M sub tau plus, A tau minus, without dissociation. I mean, like they start with it. It's like they need to write these books so that it's it's like things need to be like technically correct, but sometimes it's not said. Yeah, it's not said in a way that makes English or makes sense. It makes English.
Makes English.
Makes English.
The irony of speaking poorly and saying things that, no, it's true. It's true. I see that's also my, feeling about it, is using plain language as much as possible. I mean, there is technical jargon associated with our field and, well, frankly, any technical field. And so fair enough, those things are part of the territory, whatever you'd say. So it's reasonable to expect that you will read and hear technical language, but when possible, speak clearly and use language that's more easily understood. I feel that way, irrespective of your education level. It's way better to get your message across, to get complex subjects, like especially electrochemistry. It's hard and complex to get those kinds of ideas across. Using plain language is helpful, I suppose, especially as it comes to the research stuff too, because a lot of the times it's like you're just fumbling around. And that's the thing too, what you said too, Alex, it's like you can even read stuff, and then when you get in the lab, you forget everything you read. It's like, it's like, oh, I know all these things, and then it's like I'm clicking buttons in the laboratory and I don't know what I'm doing. Like that, no matter what you read, once you get in the laboratory, a lot of times it just goes out the window because you're like, I don't know what's going on.
Yeah.
Yeah.
Let's see. Actually, so hopefully B&B, that is a little helpful. I think we could probably ramble on at length, which we probably will continue to ramble on because some of the next few questions are more about how electrochemistry is difficult. But Dooley says, as a side, is there a way to electrochemically plate my eggshells to impart a color to their surface?
This is an advanced Easter question.
Yeah.
Eggshells are calcium something, right?
I think so.
It's not calcium carbonate, is it? Or is it calcium carbonate?
I think it's calcium chloride, maybe. I'm not so sure.
Yeah, actually, I don't know what.
Forcibly embed metal ions to plate it. Yeah, you need something to.
They're not conductive. I don't think eggshells are electrically conductive. Like calcium.
I think so.
Calcium salts or calcium, whatever calcium material is eggshells made out of. All right, I'm figuring out what are eggshells made out of.
Yeah.
What chemical compound eggshells? It's calcium something.
Yeah.
Calcium carbonate.
Oh, it is calcium carbonate.
It's calcium carbonate.
Oh, interesting. I guess that makes sense.
Calcium carbonate is essentially, I think, a mostly insoluble salt. Right? It's pretty insoluble. That's why that's why they won't dissolve in water just by themselves.
Oh yeah.
Right. I mean. So, and it's not calcium carbonate. It's not it's an insulator, I believe. It's not a conductor. So you can't just connect it to a potentiostat and plate it with some color. Maybe if you apply a high enough, maybe if you connect it to your potentiostat anyway, and you just apply a really high voltage, you'll anodize it the way titanium anodizes. You know what I mean? And it'll just start turning different colors. Because when you anodize metal at tens of volts, really high voltages, it turns blue and then green and yellow and all kinds of fun stuff. So I would never recommend you do anything dangerous. But if someone happened to connect a power supply to an eggshell and just ramp up the voltage, I wonder what would happen.
This reminds me of our Nyhouse said that they tried to electrocute a pickle. It was not a good thing.
Yeah, that's
don't want to do it.
But that works because it's full of electrolyte.
Yeah,
it's full of vinegar.
Because apparently it smells really bad.
It smells terrible. I'm sure.
Yeah,
and plus that's a waste of a perfectly good pickle.
That's also
pickles are delicious, and that's it's criminal.
Yeah,
but it is entertaining.
It's entertaining.
Yeah, as long as you do it behind a screen, so you don't have to smell it, or in a box. You know what I mean? To keep the smell out. Yeah, they destroyed a pickle.
Yeah,
electrocuted a pickle.
I guess SMY SHK is asking, why is electrochemistry so difficult? Until we get a new question, we can rant about this at length, or at least for a few minutes.
Why is it? This is a complaining session. Why is it so difficult?
Yeah, it's almost the same. I mean, it kind of goes back to why it's hard to find a good book on electrochemistry. I think that electrochemistry, sometimes things are difficult because they're either not taught well or there's not enough education on it. Electrochemistry, in my opinion, is difficult because, first off, there's a lot of jargon. There's just a lot of terminology that people don't know. And from a chemistry background, we rarely use units like current and volts in any clear way. Most of the time, you're using units like moles or joules, kilojoules per mole, wave numbers. There's a lot of light,
Kelvin.
Temperature, Kelvin, and all those things are they're very physical. You can see it in many ways. You can measure the heat that comes out, and it's also a very absolute type of thing. But electrochemistry involves voltage, which is a relative quantity, and then current it's not like moles of something. It's like a changing thing. It's like coulombs per unit time. So there's a lot of electrical engineering. There's a lot of kind of circuits that you need to know and understand. And if you're a chemist, you rarely get that kind of training. Even if you take physics like physics 2 or something that covers circuits, it's rare that you're going to actually like understand some of that stuff. I think that's one of the main reasons why it's very difficult, is because there's just these two opposite fields, like chemistry and like electrical engineering and electronics, and those rarely talk to each other, and they rarely kind of make sense. And even if you had a very good understanding of chemistry and a very good understanding of electronics, when you mix the two together, you get the most bizarre, crazy things that happen. Nothing acts like a perfect resistor. Nothing acts like a perfect capacitor. We just use these as models. Like a cyclic voltammogram of like a reversible 1 electron transfer, that's like a variable resistor that changes its composition. So it's SMY is saying that they I'm a chemist. Yeah. So you have all these like electronic components and stuff, and then understanding like the system, what does potential really mean? Those are all things that like I've struggled with and stuff like that. So yeah, that's my rant about why electrochemistry is so
I also think
difficult.
it's hard from the perspective that you have kind of what I was just talking about before. You got two competing, and sometimes they work together, aspects of it, which is practical and theory, research, and then the knowledge. So like you have the difficulty of just understanding what potential is and what current is and what all the different theoretical things are. And then you have, if you even grasp that, whether you grasp all of those theoretical concepts well or not, the practical application of doing them is also really hard. So it's like, just not all chemistry, like plain chemistry, is easy. Okay. But just as a random example, it's like, you can learn about acid-base reactions, and it's hard depending on your, interest in chemistry. Let's just say, okay, so,
Yeah.
but like, you're learning about stoichiometry and neutralization and chemical reactions or whatever. And so maybe that's hard for you, but if you get that, well, the practical thing of it is dump some acid and dump some base together and, put phenolphthalein in it and watch it turn pink if it's basic or what, it's like, some of this is not that hard. Do titration and watch a thing. It's like, that's not that hard. High school chemistry classes do that all the time. It's not like physically that difficult, but there's a reason why almost no high school students or even undergraduates do any practical electrochemistry. It's physically hard. So in addition to the fact that all the things you said, like just understanding all the stuff, whether it's because there isn't good education or because it's just fundamentally hard to like grasp these concepts, then the practical, there is no electrochemistry experiment almost, like, not other than like a dummy cell, like a real, solution-based electrochemistry. There's almost no real electrochemistry experiment that's easy. There are easier ones.
Yeah.
Right. But like all of them require some amount of like, well, make sure the thing is positioned just this right, or make sure the clip is here, because otherwise it'll be terrible. It won't work. Like, and consistency is hard, So it's like, you got both of them. You come at that from both sides. The conceptual and the practical are both hard, and it's like, that's why, I guess too, that's why it's tricky. It's like people are looking for, I don't know, for answers on the theoretical stuff. And then you're looking for help on how to get your experiments to work. And it's like, I want both of those things, and they're both difficult, Studied organic chemistry is your major. Your research is on water splitting. Yeah. Water splitting is also tough. Water splitting is a hard thing to study, especially if you're doing oxygen evolution or hydrogen evolution, because now you're mixing in another phase, right? You've got solution phase electrochemistry, generating gas, breaking up the interface, making a reaction harder. Yeah, it's hard. It's hard.
Electrochemistry also tends to be more of a analytical and physical chemistry side. Organic, like inorganic chemists use some electrochemistry, but they mostly they just care about their complexes and what the complexes are doing. And organic chemists mostly use electrochemistry as a tool to oxidize or reduce something. They use it as an oxidizing agent or a reducing agent. But then the physical chemists and the analytical chemists are like, oh, I need to understand the details of measuring charge, or like what fundamental processes are actually happening at the surface. And so to a degree, like I've spoken to some inorganic chemists and they're just like, yep, I get peaks in my CV and that's all I care about. And they're reversible, and they don't care at all about like double layer charging, or they do enough IR compensation so the solution, so the peak splitting is normal, and that's like it. They don't want to know more and more about like, hey, your double layer capacitance is going to be different depending on the concentration of the electrolyte you use.
Yeah,
it's like I don't care about that.
But to a certain extent, that's also, I don't know, reasonable, right? Like you have a purpose for doing electrochemistry practically, to get these peaks, and you need whatever the analysis is. And so in those instances, I think it's good if you do have the ability to get competent data out of it. Like that's excellent, right? Yeah, that's half of the hard part. So but the problem comes when then you reach a point you have to write a paper about it, or you have to explain it as part of your thesis or your presentation. Then you have to get the other part, the understanding and the explanations, and that's just that part's just also really hard. And that's unfortunate too, because that's what the PhD is for, right? Like the P in PhD stands for philosophy for a reason. It's you're learning like how to think and how to think about things critically and how to understand phenomena and what's going on. And so, if you're getting a PhD and it involves electrochemistry, it's incumbent that you learn some of those things, which sucks because they're hard. So, I mean, the best that we can do for you specifically, or anybody who's feeling like it's hard and you're looking for answers, is, well, we do this every Friday to try to answer those questions, but also to just be commiserate with you, I guess, right? Just to some extent, we don't always know the answer to every question. But the best that we can do is we're all a community together, and we're all sometimes equally, confused, I guess, or something like that. Electrochemistry is hard. We've all been through it, I guess, is the point too. So you don't have to feel alone if you are feeling sort of lost, right? We've all been there. We've all been in that place in graduate school, or even like yesterday, where we were trying to understand some concept and just shaking our head and being like, I don't know why I can't understand this, and I don't know if there's enough resources out there. And you just, that's normal, I suppose. If it's worth anything, don't feel despair, right? You're not alone. This is a common thing with research in particular, and electrochemistry specifically, for sure.
I'd recommend also, as you're studying, write questions down, and then you can make a comment on the video or just on an upcoming live stream, and then we can take a look at it. And especially if it's a conceptual thing, like, hey, I was reading this and they said this thing and this doesn't make any sense, we can try to answer that or provide some clarity to it. So that's it. All right. Well,
I think we can wrap it up.
I think so.
Wrap it up. Yeah, I think for sure that the holiday weekend is why we've not been as bombarded with questions, which has been nice. We've been now allowed to sort of ramble about other things, which is also kind of nice. I don't mind it so much. Maybe everybody out there minds it because you don't want to hear us ramble.
Yeah.
But that's too bad. So anyway, given that it is a holiday weekend, I suppose if you're doing anything, have a wonderful holiday weekend. And are we here next week? We're here next week.
Yeah, we're here next week.
I don't know what's going on.
Yeah, that's okay.
That's why Alex is here. So have a great weekend, everybody, holiday or not, and we will see everybody next week. Take care.
Bye.